Hello and welcome. In continuation with our series, we will study non-aqueous solvents in this lecture. As the name goes, non-aqueous solvents are those solvents which are excluded of water. They are required to carry out reactions of some non-polar substances which do not dissolve in water, since water is polar. When we come to the discussion of some properties of water, water is colorless, it's odorless, has low viscosity, long liquid range, is easily purified, non-corrosive, has high polar nature, is stable, it is non-inflammable, non-explosive, and has high dipole moment and a high dielectric constant. So water having so many properties, it is considered as a universal solvent. However, water cannot be used as a solvent for certain reactions because some non-polar substances do not dissolve in water. Also, water is reactive. It can cause hydrolysis and is amphiprotic, that is, it causes leveling effect on the solvents. When we talk about leveling effect, then in water we are unable to determine which acid is stronger, as in water all acids are fully dissociated and hence all acids, whether it is hydrochloric acid or sulfuric acid or any of the chloric acids, those acids are all considered to be equally strong in water since they are all fully dissociated in water. Coming to the various type of solvents which exist, there are protonic solvents as well as aprotic solvents. Protonic solvents are those solvents from where a proton can be derived under ordinary conditions. By ordinary conditions, we mean in a normal temperature, in a normal pressure reactions. For example, water. Water is a solvent from which protons can be easily derived. Aprotic solvents are those solvents from which protons cannot be derived under ordinary conditions. For example, liquid sulfur dioxide. Liquid sulfur dioxide, as we can see, does not contain a proton. Hence, it cannot give a proton under ordinary conditions. Therefore, it is termed as an aprotic solvent. Solvents can further be classified as acidic, basic, and amphiprotic solvents. Water is a leveling solvent for all acids and bases. A differentiating solvent for acids is glacial acetic acid, and differentiating solvent for bases is liquid ammonia. When we talk about differentiating solvents, then differentiating solvents are those solvents in which the acid, for example, in case of glacial acetic acid, all acids can be differentiated according to their strength. That is, we can tell which of the acid is stronger and which is weaker in glacial acetic acid. Similarly, liquid ammonia is a differentiating solvent, or as we say, it differentiates the strength of bases in itself. Substances with high dielectric constant have a good tendency to align themselves along the electric field, and so they help to dissolve ionic substances. Water has a high dielectric constant of 80. When we say water has a high dielectric constant, that means water is a very good solvent since it has a capability that it helps to align all the ionic substances along its electric field and hence helps to dissolve them. Similarly, when we say water is a polar solvent, and it helps to dissolve all the polar solids or substances or solutes. Then it follows the property of like dissolves like, wherein a polar solvent dissolves a polar solute. When we talk about the dissolution of a particular solute in a solvent, then we discuss the forces of attraction which are existing between the substance which has to be dissolved and the solvent in which the substance has to be dissolved. For that, we need to study an equation where F is equal to Q1 into Q2 upon R square, where F is the force of attraction between the opposite charges. By opposite charges, we understand the ionic solute, like for example, if we consider sodium chloride, then in case of sodium chloride, sodium ions and chloride ions which have opposite charges but have a certain force of attraction between them because the charges are unlike. So in a medium of a high dielectric constant, for example, F will be equal to Q1 into Q2 upon E into R square, where E is the dielectric constant. Q1 and Q2 are the charges and R is the interionic distance. So, if the dielectric constant of a solvent is high, F will be small, as can be seen since E is in the denominator. So, if E is more, F will be less. That is, the force of attraction between oppositely charged ions will be less and the ionization of the solute will occur fast in that particular solvent. So, if the dielectric constant of a solvent is high, then it will be able to dissociate a particular solute very easily because of the formula which we have just studied. Coming to the discussion of polar solvents, all polar solvents are aggregated or in the form of clusters. These clusters in the form of rings or chains of molecules are formed due to electrostatic attraction. Arrays or long chains, as we say, may also be formed, and the figure below shows us an array of certain molecules or polar solvents. A non-polar solute is not able to diminish the attraction between the oppositely charged species and is unable to break the aggregation of a polar solvent and thus cannot enter the interstices of the polar solvent. Since a non-polar solute does not have a similar structure as of a polar solvent, so it does not offer a competing attraction, or as we say, it is not able to break the aggregation or the cluster we have just seen of a polar solvent, and once it is not able to break this cluster, it will not be able to enter the interstices of this solvent, and hence a non-polar solute will not get dissolved in the polar solvent. Similarly, a polar solute is unable to break the array of a non-polar solvent. However, a polar solute is able to break the array of a polar solvent. Hence, the property of like dissolves like, that is, a polar solute will dissolve in a polar solvent and a non-polar solute will dissolve in a non-polar solvent. Water is able to dissolve both ionic and polar covalent substances. Therefore, water is termed as a polar solvent. In this case, both the solute and the solvent offer competing attraction and break each other's bound aggregate. That is, the ionic solute is also in the form of a cluster, or a polar covalent substance is also in the form of a cluster. The polar solvent or water is also existing in the form of a cluster, because all the H2O molecules are attracted to each other with the help of hydrogen bonds. So, since the structure of both ionic as well as polar covalent substances is the same and it is similar to that of water, the aggregation is similar to that of water, so both of them can compete with the structure of water, break the bound aggregate of water, and hence enter the interstitial spaces and get dissolved in it. Moving on to the classification of solvents. Solvents can be classified as number 1, ionizing and non-ionizing solvents. Ionizing solvents are those which offer a medium for ionic reactions to take place. For example, water or sulfur dioxide. Non-ionizing solvents are those which do not offer a medium for ionic reactions to take place. For example, benzene and carbon tetrachloride. So basically, when we are talking about ionizing and non-ionizing solvents, then ionizing solvents are those which auto-ionize, non-ionizing solvents are those which do not auto-ionize. By the word auto-ionization, we understand that, for example, in case of water, water auto-ionizes to give hydronium ion and hydroxide ion. So we can say that ionizing solvents undergo slight auto-ionization. Similarly, ammonia, it also undergoes auto-ionization to produce ammonium ions and amide ions. That means they themselves ionize to give their respective ions, and hence they are behaving as ionizing solvents and offer a medium for ionic reactions because they themselves split up into their respective ions. The second classification of solvents, as we know, is the protonic and aprotic solvents. Protonic solvents are those from which a proton can be derived under ordinary conditions. For example, water, liquid ammonia and glacial acetic acid. And as we know, all of these liquids contain protons, and hence protons can be derived from them easily. Aprotic solvents are those from which protons cannot be ordinarily derived. For example, liquid sulfur dioxide. Liquid sulfur dioxide does not contain a proton, and benzene. Benzene although contains hydrogens, but those hydrogens cannot be derived under ordinary conditions because of the nature of benzene. Protonic solvents can be further classified into acidic, basic and amphiprotic solvents based on the Bronsted-Lowry concept of acids and bases. There are two concepts of acids and bases: the Lewis acid concept, which is based on the give and take of electrons, and the Bronsted-Lowry concept, which is based on the give and take of protons. So, according to the Bronsted-Lowry concept, an acid is the one which has a marked tendency to donate protons. So, therefore, acidic solvents have a tendency to donate protons. For example, glacial acetic acid. Similarly, basic solvents are those which have a marked tendency to accept protons. For example, liquid ammonia. Acetic acid can donate its proton to give acetate ion. Ammonia can accept a proton to form ammonium ion. Amphiprotic solvents are those which can function both as a proton acceptor and a proton donor. That means it has a function or a property of both, and it can accept electrons, or it can donate protons, or it can accept protons as well as donate protons. For example, water and certain lower alcohols which have less molecular weights. These solvents have a leveling effect on the strength of both acids and bases. So amphiprotic solvents, when we talk about water or lower alcohols, they level the strength of both acids and bases. That is, we are not able to distinguish between the strengths of many acids in water and also the strength of many bases in water. And the reaction which is given below, in which water is reacting with hydrochloric acid, giving chloride ions and hydronium ions. In this case, hydrochloric acid is the acid, water is functioning as a base over here, giving chloride ion which is termed as the conjugate base, and hydronium ion which is termed as the conjugate acid. Water is a stronger base than the conjugate base of the acid. So the conjugate base of the acid is chloride in this reaction. Water is a stronger base than chloride. Hence, the reverse reaction does not occur. That means the reaction which we have just seen proceeds to completion. Equilibrium is completely towards the right and there is complete ionization. Thus, water levels off the strength of all common mineral acids. So, if we talk about any other acid apart from HCl, in that case also hydronium ions or the conjugate acid will be produced, and the conjugate base which will be produced will be definitely weaker than water as a base, and hence all the acids will be completely ionized in water, making water as a leveling solvent and not being able to distinguish between the strength of various acids, since they all have proceeded towards complete ionization. However, glacial acetic acid can be used to differentiate between the strength of acids. So, as a reaction which shows hydrochloric acid reacting with acetic acid, giving chloride ions, and one of the protons gets attached to the acetate ions, giving CH3COOH2+. HCl is a weak electrolyte in acetic acid. Acetic acid is itself acidic, so it behaves as a weak base. So what do we understand from this reaction is that since acetic acid is a weak acid, upon reacting with hydrochloric acid, it behaves as a weak base, and it tells us that HCl is a stronger acid than acetic acid. Based on the position of equilibrium in an acidic solvent, mineral acids can be graded according to their strength. So, as we talk about these acids, given as perchloric acid, HClO4 is the strongest acid. After that, sulfuric acid, which is slightly weaker, and then HCl, hydrochloric acid and nitric acid, which are weaker than the previous two but are of approximately equal strengths. Acetic acid on reaction with perchloric acid gives perchlorate ion along with CH3COOH2+. In the previous reaction what we studied, HCl was giving chloride ions, perchloric acid is giving perchlorate ions. So, perchloric acid is strong acid in acetic acid since complete dissociation is taking place. Ammonia in presence of water gives ammonium ions and hydroxide ions. This reaction also proceeds to complete dissociation. For protonic systems, basic solvents are differentiating for bases and acidic solvents are differentiating for acids. And by this statement we mean that basic solvents are able to distinguish between the strength of various other bases, and acidic solvents are able to distinguish between the strength of various other acids. For example, acetic acid, which is an acidic solvent, is able to differentiate between the strengths of various acids, as we have just studied, and liquid ammonia, which is a basic solvent, is able to distinguish between the strength of various bases. A basic solvent has even a greater leveling effect on the strength of acids than water. By this statement, we mean that water which is behaving as a leveling solvent for various acids and even bases, if those acids are taken in a particular basic solvent, then that basic solvent will further level the strength of all the acids. For example, if we consider all the acids like perchloric acid or sulfuric acid or hydrochloric acid, nitric acid, and so on, then these acids will be almost of the similar strength in a basic solvent, for example, liquid ammonia. These acids will be also of similar strength in water, but still we can grade them to their acidic strengths to some extent in water, but in a basic solvent all the acids will be of equal strength. So, as we say that a basic solvent has a greater leveling effect on the strength of acids than water, and the example which we give for this is that acetic acid is a weak acid in water, but it becomes a strong acid in liquid ammonia. Thank you so much.